Dear students, in today's lecture we will discuss about DC motors. In the case of DC motors, the main topics which we will discuss today are introduction to DC motors, the equivalent circuit of a DC motor, the magnetization curve of DC machine, and the 4 to 5 types of DC motors. First of all, we discuss about the introduction to DC machines. DC machines are generators that convert mechanical energy to DC electrical energy, and these DC machines are also motors that convert DC electrical energy to mechanical energy. So most DC machines are like AC machines in the sense that they have AC voltages and currents within them. DC machines have a DC output only because a mechanism exists that converts the internal AC voltages to DC voltages at their terminals. So it means that the internal mechanism of AC machines and DC machines are quite similar. Since the mechanism is called commutator, DC machinery is also known as commutating machinery. Now it can be seen that there are two curved pole faces. This is curved south pole and this is curved north pole. And then there is a simple loop in between these curved pole faces. And this loop is rotating. And the loop is also shown over here. If we see from the top view, this is our loop and this is one magnetic pole and this is another magnetic pole. So if we want to find the E induced on this loop, it would be V cross P into L. But we will find this E induced separately for all the four sides of the loop. One side, second, third and fourth. Two of the sides would get the value 2RLB omega if we combine them, and the other two would have zero value. So if they are under the pole faces, they would have the value. If beyond the pole faces, then it would have zero value. Now the induced voltage in that loop is something like this, which is kind of a sinusoidal waveform. But there are some other terms in which the induced voltage can be written. So if it is considered like A is equal to pi r L, then this 2 RL B omega can be written in terms of AP. Similarly, if we know that flux is equal to AP into B, then these equations of E induced can further be simplified, and the answer would be that E induced is equal to 2 over pi phi omega. So this would be the totally induced of the two sides, and the other two sides would be 0. So all the four sides would be contributing this 2 over pi phi omega. Now we want to get this DC voltage out of that rotating loop. This can be obtained by these brushes and commutator, and these brushes are further connected with a circuit, and this DC voltage would be something like this. They would have a small glitch at every cycle change, otherwise it would be a positive DC voltage. This is again the same circuit. In this diagram it is shown how the force has been applied on the loop and how the torque can be obtained. So torque can also be obtained in a similar fashion, that it would be obtained for each side of the loop separately and then combined to get the induced torque. So similarly, it can also be simplified if we put AP is equal to pi RL and phi is equal to APB. Now this is the mechanism of DC motors, that when electric current in red, this is the electric current, passes through a coil in a magnetic field, blue magnetic field, the magnetic force, this green one, the magnetic force produces a torque which turns the DC motor. So there would be a torque produced which will turn the DC motor. Now it can be seen from this uh, animated diagram, that how the loop is moving and how this loop is producing DC voltage and current towards the circuit connected with this loop, and this circuit is connected with some rings and brushes which completes the circuit. So if we want to know about the equivalent circuit of a DC motor, it is quite simple, that it can be obtained by using the simple diagram, in which it can be seen that EA is equal to phi omega and K is a constant, K phi omega, and tau is equal to K phi I. So this is I and this is EA. Similarly, this is I and this is EA, and this is a flexible resistor which was in different parts in previous diagram, and in this diagram it has been shown as a resistor which can be changed according to the requirement. Now we look about the magnetization curve of a DC machine. So in a DC machine, magnetomotive force, which is shown on x-axis, and this is phi flux on y-axis. So phi is directly proportional to F up to some extent. At some value, this phi would saturate and become horizontal and a saturated curve. Similarly, we know that this phi is like EA is dependent on this phi, if you see from this equation. So if EA is dependent on this phi, the graph of EA would also be similar if we draw this EA on y-axis and current IF on x-axis. We again know that by increasing the current we are increasing the voltage linearly up to some extent, and then this EA would again saturate similar to that phi. Now we come to know about types of DC motors. There are 5 major types of DC motors which we will discuss in next few slides. First one is separately excited DC motor, then the shunt DC motor, the permanent magnet DC motor, the series DC motor, the compounded DC motor. We will see their diagrams and brief overview in next few slides. First of all, we talk about the separately excited DC motors. In separately excited DC motors, we know that we have two circuits, and we can find that I of F on left circuit, the current would be equal to V of F, this voltage, or R of F, this resistance. Similarly, this terminal voltage Vt would be equal to EA, this voltage, and the voltage across this resistor. The voltage across this resistor would be IA RA. So we can find the value of Vt. Now we come to value of IL, which is equal to IA. It can be seen from here. And it is written that sometimes these two resistances are lumped together and called RF, like we have discussed, and we have used RF in this case while finding the current IF. Now we come to know about the shunt DC motors. In shunt DC motors, the one part is connected to other second part in a shunt way or a parallel connected way, something like this. This part is shunted with the previous half part of the motors. Similarly, by Kirchhoff's current and voltage laws, these values can be obtained from this circuit quite easily. Now the series DC motors. In series DC motors, the resistance and inductance are connected in series rather than connecting them in a shunt way. Similarly, IA and VT terminal voltage can be obtained similar as we considered in the first case. We can easily use Kirchhoff's current and Kirchhoff's voltage law to find these variables. Now we come to know about the compounded DC motor. The compounded DC motor is a motor with both a shunt and a series field. A current flowing into a dot produces positive magnetomotive force. So these are the dots. If the current flows into the dots on both coils, the resulting MMF adds to produce a larger MMF. This situation is known as cumulative compounding. So in this case, it is cumulative compounding, and in this case it is differentially compounding. If the current flows into the dot on one field coil and out of the dot on the other field coil, the resulting magnetic MMF would subtract, and the figure round dots correspond to cumulative compounding and the square correspond to differential compounding. Now we find another type of DC motors in which two permanent magnets are brought close to each other to form a DC motor. In this case, one permanent magnet is used as a rotor and the other permanent magnet is brought closer to the previous one time as a south pole, and in second cycle the nearby magnet comes as a north pole. So the permanent magnet which is brought closer to another permanent magnet is switching its poles on every cycle, and this switching would generate a circular motion in the first magnet, which will become a DC motor. So we discussed a few points of this. A permanent magnet DC motor is a motor whose poles are made of permanent magnets. permanent magnet DC motor offer number of benefits compared with the shunt DC motors in some applications. So these are the benefits. Since these motors do not require field circuit, they don't have the field circuit copper losses associated with the shunt DC motors in other simple cases. Because no field windings are required, they can be smaller than the corresponding shunt DC motors. So this size is quite smaller than other shunt DC motors. Permanent magnet DC motors are especially common in smaller fractional and subfractional horsepower size where the expense and space of separate field circuit cannot be justified. So these are some applications and advantages of the permanent magnet DC motor. So this is for today. Thank you.